video, so I'll record on this computer. And pretty simple problem. Um, Not a lot of problems that I can put on homework or exams result from that, but it is something that's worth seeing because it's one of those hopefully aha moments in your physics education. And so that's the main part of today's topic. I did want to I also want to work a problem that's an example. It's actually a question that came up in one of the breakout rooms, I guess last Friday, because we were looking at the ability to convert between mass and energy, which is part of our relativistic energy ideas that mass and energy are interchangeable. If they talk about conservation of mass, well, you got to say something like it's the conservation of mass energy. And of course, we've got all our new kinetic energy in special relativity, total energy in special relativity. And the question that was asked is, so you're saying that you can just make mass out of energy or make energy out of mass? And the answer is yes, you can. And I will tell you, we're moving into chapter 3 next class, and we'll be looking at all kinds of phenomena that happened in the early 1900s that led people who studied classical physics to go, maybe we don't know everything. And one of the experiments we'll look at is something called pair production and pair annihilation. Pair production will actually, out of energy, in uh, electromagnetic energy, will create two particles, an electron and what's called a positron, which we'll talk about later. Okay, and vice versa. I can have two particles with mass, an electron and a positron. They could come together, annihilate each other, and create energy. And so today we're going to look at another example of that, just because it was an example in a book, so we'll do it. And I'm going to try to do my work here in OneNote, and I'll try to keep it smooth. If I need help, I may ask you all, what do I do in OneNote when I want to do this? So let me share my screen with you via AirPlay. And hopefully, one of the things I noticed when I did do the screen mirroring and sharing the screen, it resizes it on my tablet. So hopefully I'll still be able to, yeah, it didn't do too bad. It cut it down a little bit. Hopefully you're seeing my first slide, which is this idea of binding energy. Okay. And so as we said, come on. Oh, I got to turn my stylus on. These are just little things. Okay. We said that energy is converted to mass according to E equals mc squared, probably one of the most famous physics equations ever. And there's an equivalence. And when we either fuse particles together to make other particles, or fission particles together to get energy out, fission a particle apart to get energy out, we play with this thing called binding energy. Okay, and we're going to look mostly at the fusion side, but I can tell you I worked in nuclear power for many years, operating naval reactors, and fission, the other side, you have this binding energy being released. Okay, as opposed to in fusion, like in the sun, binding energy being let go when the creation occurs. The difference between fusion and fission is, as I guess the names almost say, when you bring two things together and you get a third thing. Okay, that you're fusing those things, and sometimes energy is released. On the other hand, fission, you'd have one thing that breaks up into multiple things, and again, energy is released. The energy that's released we call the binding energy. Okay, and we sometimes think of it as a potential energy associated with the force that's keeping the system together. And that's a lot of words that aren't awfully useful. I always got to remember to go to the little finger. So here's kind of an equation that talks about it. If I have the bound thing, okay, after I've fused two things together, like I don't know, hydrogen and deuterium or something, and I fuse it, and I'm going to get some other piece, or maybe I fuse together some neutrons and some protons, and I get an alpha particle. Okay, the mass of the bound system times the speed of light doesn't add up to be the sum of the particles that I fused together. There's a little defect, a little decrement between those two. Okay, you would expect that the mass of the bound system is times the speed of light squared would just be the sum of the mass of all the individual particles times the speed of light squared, and it's not. In fact, there is this extra mass left over, which is called the binding energy, which is given off as heat. And of course, that's the engine of the sun, right? We make helium out of hydrogen, and the helium actually has more mass than the resultant, the hydrogen actually has more mass. The hydrogen pieces that go together to make helium actually have more mass than the helium that they create. And so that excess mass converts to energy. It's referred to as binding energy that keeps the helium together, but it is released, and that's what causes the sun to be hot. And so our job is often to find that binding energy, which means we'll add up the sum of the pieces that we put together, the mass times the speed of light squared for those pieces, and compare that to the mass of the system that we put together, like helium or whatever, times the speed of light squared, to find that difference, because that's energy that's released. And that is what we refer to as the binding energy. It is what keeps the thing that we put together from flying apart, because we bound it together. And maybe the best way to work that, always forget to do that, is to do an example. And it is actually example 216 in your book. And so I've given you all the pieces here, okay? We're making a helium atom, right? Because right here you can see, oops, I missed. We're given the mass of a proton, the mass of a neutron, the mass of an electron. So we've got the component pieces that make up helium. And I've given you a kind of a lousy looking sketch of a helium atom. And of course, we have the mass of helium. And they're given in this thing called an atomic mass unit. And hopefully you saw in one of the videos I recorded what that is. That's the number that you pull off the periodic table. Like for carbon, you pull off 12. That's atomic mass units. It is equal to the number of grams in 1 mole of those things. In this case, protons or neutrons or electrons, okay? And so our goal here is to figure out what the difference is between MC squared for the component parts and MC squared for the resultant helium. And I'm going to use that guy right there, the 931.5 MeV per C squared, as a conversion factor commonly accepted for an atomic mass unit, okay? So I'll come back and forth if I need to. What I've done is I've given myself a little piece of graph paper in order to work this. And so I guess the first thing I want to do is figure out what is the sum of the component pieces, okay? And I'm summing over I pieces here. There's 3 things: protons, neutrons, and electrons. So what is MC squared for those things if you add them all up? And so I guess it would be the mass, the order I did them was an electron times C squared plus the mass of a proton times C squared plus the mass of a neutron times C squared. And when I did that, let's see, I'll factor out the C squared, so I don't have to multiply it out once. I've got in a helium, I have 2 electrons. So 2, if you go to the previous slide or look it up in a table somewhere, 0.00549 atomic mass units. Okay, plus for a proton, I have I should be multiplying by 2, shouldn't I, first, just to be consistent. 2 times 1.007276. And of course, I got to look these things up. That's not something I have memorized. Okay, and then I'll bring on the next page, the next line, plus 2 times, let's see, a neutron, 1.008665, 1.008665 AMU, and then close the square bracket. Now, I'm in units that I don't like. So right now, let's say, okay, remember that there is 931.5 MeV per C squared is 1 AMU, okay? So I should really go, that's equal to 1 AMU. And so that ratio right there is 1, so I haven't changed anything. Okay, that's just a conversion factor. And so this AMU here cancels that one, and that one, right? And then here's the part that may have been new when we first talked about it. The C squared in that unit right there actually cancels the C squared in the equation, which I wrote out front. And so hopefully that's helpful. And if I now run all this into my calculator, what I get for the total mass of the constituent parts of a helium atom, the answer is 3756 point, let's see, what I'm, 0.7 MeV. Okay, that's the energy of the constituent parts, or the mass energy of constituent parts. One thing I do want you to notice, look how much bigger the mass of a proton or a neutron is compared to an electron. It's like 1,836 more times more great. But the mass of the proton and the neutron fairly close. Neutron's a little bit bigger, isn't it? Just slightly bigger. Okay, but I almost could have deleted the mass of the electrons and probably would have still gotten a reasonably close number, because they're different by 3 orders of magnitude. In any event, that's the constituent parts if I look at them. And so now, how does that compare? And by the way, just those are the numbers right up there. I just pulled those numbers right down and used them. And I guess the next question is, what is the mass energy of the helium once it's put together? So what is, and I don't know why I'm writing E. Let's go with mass of the helium times c squared. How does it compare? Okay, well, it is, according to my chart right there, 4.002603 atomic mass units. Okay, that's the mass in it in AMU, and then I'm multiplying by c squared. And then, of course, I've got my unit conversion, which is 931.5 MeV per c squared for every atomic mass unit. Okay, so that cancels that, and again, c squared cancels that. And if I do this in my calculator, I got 3728.4 MeV once I put the helium together out of its 6 constituent parts, right? 2 protons, 2 neutrons, 2 electrons. So if you look at the difference between the two, okay, just subtract them, you'll notice that the constituent parts have a greater energy by, if I did the calculation right, looks like 28.3 MeV. Okay, that's what we call the binding energy. And so when we convert 2 electrons, 2 protons, and 2 neutrons into helium, we liberate, we say, about 28.3 MeV. That's the binding energy then that keeps the helium nucleus and the helium atom from flying apart. In fact, if you want to take a helium atom and break it up back into neutrons, protons, and electrons, you'd have to put back in at least 28.3 MeV to get the mass you need to break them up into their constituent parts. Okay, generally that's not the way it works. If we could only figure out how to do this in a controlled fashion here on Earth, like it's done in the sun, boy, we'd be set, wouldn't we? We'd solve any energy problems. Any questions on this? I don't see anybody asking anything in chat, so it really is just a conversion with these units. Hopefully you see that this problem would have been a real bear had I gone the other direction and used, instead of AMUs and MEVs per c squared for my units, if I'd have gone and used kilograms and then got joules out of that, and then converted that to electron volts, or maybe left it in joules, it would have been a much more difficult calculation to do, as I did it here, fairly straightforward. All right, everybody good on this? All right, you do have a worksheet problem which mirrors this. It's a slightly different set of constituents going into another part. If we got time at the end, we'll talk about that, but we're going to leave binding energy and get on to the real topic for today, which is electromagnetism and relativity. And what we're going to show is what Einstein proposed is that there really is no such difference as the one we discussed in Physics 2. No such difference as a distinction between an electric field and a magnetic field. Okay, Einstein was convinced that they're exactly the same thing in nature's world. We define them differently, but according to the universe, they're exactly the same field, just viewed from two separate reference frames. Exactly what we've been talking about. Okay, that's it. Bottom line, Einstein believed that Maxwell's equations were correct in any inertial reference frame, correct in the sense that it predicted a speed of light that didn't vary with reference frame. All it varied with was two physical constants, which didn't vary with reference frame. Okay, permeability of free space and permittivity of free space. That everybody wants to use Coulomb's constant and an equivalent magnetic Coulomb's constant, but they're not the fundamental constants that seem to be pervasive and necessary to describe the universe we live in. Okay, that's it. Moving on then. Let's do a problem in two ways. Okay, and it's the simplest problem I can think of because we can pretty easily calculate the electric field around a wire that has charges in it, and we can figure out what the magnetic field is around a wire that has moving charges in it. Okay, currents. And we, if you don't remember how to do that, don't admit it right now. I'm going to go over a couple examples of how to get these fields as we did in physics 2. And you'll make me feel bad if you tell me you don't remember any of this. All right. But if you look, there's actually two sets of diagrams here. The top above this line right here, this is how we're going to view the world from what we call the lab frame, the so-called K frame, right? Okay, or the lab frame. And then in the bottom here, this is going to be in the moving frame or the K prime frame. And moving with what? This moving charge right here. We're going to watch it move in the lab frame. While we're stationary, that thing will be moving. And in the moving frame, we'll be moving with this moving charge up here. Okay. And so in that world, we'll be at rest moving with the thing. All right. In the lab frame, in the top diagram, which is what we'll do first here, top set of diagrams, you can see that we have electrons moving off to the right, which is exactly what we expect for a current. And of course, we define current to be the motion of positive charge carriers, the so-called holes that these electrons leave behind as they're going to the right. The vacant atom that doesn't have an electron anymore is actually going to the left. And so electrons moving to the right mean a current going to the left. And if there's a current going to the left, hopefully you remember the right-hand rule being drawn around the bottom wire right here. Okay, let's see, put your thumb in the direction the current is going in, swirl your fingers around above the wire, you'll of course have that magnetic field going into the page, right? Okay, that's good. And so let's see if that positive charge there is moving to the right in the vicinity of a magnetic field that's into the page. Bottom line is we're looking for this force right here. And so you use your right-hand rule and the fact that the force is QV cross B. QV is to the right. The magnetic field we just said is into the page. My thumb is pointing upwards, and so that's why we say the resultant force on that moving charge from this moving current, which creates a magnetic field, well, the resultant force is upwards. Okay, and I said that pretty quick. We're going to go through some of the pieces behind that. And the first thing we better do is figure out how to calculate that magnetic field around the around that wire. And we're also going to look at what the electric field is around a wire as well that has charges in it. And Maxwell's equations, the first one being Gauss's law, is how we're going to do that. The bottom equation is Ampere's law. And we're going to get both those equations in place, and then we're going to use them to describe mathematically what I just said in words just a second ago. All right, so remember what Gauss's law said about calculating the electric field around just a one-dimensional line that has charges in it, okay? And we're going to say that this line here has some amount of charge Q on it. And so that's that total charge divided by the total length. defines something that I call the linear charge density. How much the charge, how well the charge, or what number describes how the charge is spread out over the length of the total wire. We're not going to look at the total wire. I don't even know what its length is. Okay, it could be miles long, but remember, this will have units of coulombs, the unit of charge, divided by meters, right? That'll be the units on lambda. And it's a simple one-dimensional thing. We also talked about rho, which is charge per unit volume last semester, and we talked about sigma, charge per unit area, like on a plate or a sheet of charge. Okay, this time one dimension works fine. That wire that looks kind of like a cylinder, we're assuming all the charge is along a line. So coulomb per meter is what we can work with there. Okay, and in order to use Gauss's law to calculate an electric field, you may remember that you have to have a priori some idea of what the electric field looks like. Okay, and we think around a individual charge, the electric field goes out from a positive charge in all directions. And so if I've got a line of charge, we think that around positive charge, because we wrote positive right there, the electric field would be radially away from this line. If you think about like a test tube cleaning brush and the bristles on it, the electric field kind of lines up with the bristles. And the only place that would become a problem is if I ever got to the end of the wire, well, they might start bending over at the end of the wire if the wire has one. So we're going to stay away from the end so we don't have to worry about those effects. Okay, our electric field is moving directly away radially in a cylindrical coordinates sort of sense from this wire. And hopefully you've seen a little bit of cylindrical coordinates, or will shortly in your math course. And so Gauss's law, if I pick a good surface, and symmetry suggests that yellow cylinder right there, well then the electric field everywhere on the surface of that cylinder times the area has to be equal to the charge enclosed in that cylinder divided by the permittivity of free space. And you should hopefully remember that since the normal on these ends here is that way and that way, okay, outward from the ends, and the electric field, if we stay near the middle of the wire, is radially away, that dot product causes us not to have to worry about the ends. All we have to do is worry about that curved area, okay, that is the side of the cylinder. And so I can take, I'll come up over here to work it, I guess, so that you can see my whole picture. If I take E dot dA on the surface of that yellow, we call it a Gaussian surface, it would just be the unknown electric field that I'm trying to find, and then just a curved surface area, which, let's see, it is 2 times a pi times that length times the radius, right? And maybe it would have been better if I'd have written 2 pi r, the circumference, times the length, but that works, okay? All right, and then you look at the other side of Gauss's law, and you get the charge inside, the charge inside, the charge inside. Well, if I take the charge per unit length and I multiply it by the length, charge per unit length, and I multiply it by the length is talking about is that length right there, and divide that by the permittivity of free space, we see that, well, that should get us the answer, okay? How long I made the Gaussian surface doesn't seem to matter too much, does it? So the electric field here is equal to the lambda, which is what's left up there. I didn't cross it out. I crossed out the length, divided by 2 times pi times the permittivity of free space times whatever the radius is. Okay? And hopefully everybody's good with that. Nobody's chatting saying, we've never done this before, because I'd tell you, well, you have. I did it for you, for at least for 7 of you, I guess. Okay? And by the way, if you like, remember that Coulomb's constant is 1 over 4 pi epsilon 0. So I guess this would be twice Coulomb's constant times the charge per unit length, lambda, divided by the radius, if you like that form of this equation better. They're equivalent. And this is the one I'm going to use today. Okay? Hopefully no questions on that. Nothing in chat. And so we'll move on then. And let's talk about the magnetic field now. I gave myself room to work there. I think I'll be okay here too. And I want to find now, because we said these wires might let the charges start moving in one reference, in the lab reference frame anyway. And so we had Ampere's law, which allowed us to get the magnetic field. It has a similar form to it, only instead of talking about surfaces, Ampere's law deals with closed paths. You'll see that the Ampere's law integral is over a path, whereas the Gauss's law integral was over an area, right? And that's the way nature made it. We didn't do it. It just kind of worked out that way. And so the deal here, I guess, is that I have to pick a nice path, and you can see that outer dashed line is the one that's chosen. You have to make the argument that the magnetic field is the same everywhere on that path. You kind of made that same argument from symmetry on the Gaussian surface. You had to believe that the electric field was everywhere the same on that surface. And so this kind of wacky looking integral just becomes the magnetic field times the circumference of the path, right? 2 times pi times whatever the radius is. And you can see the radius is labeled right there. Well, according to Ampere, that has to be equal to the permeability of free space times the current which is enclosed by the path. And you can see all this current goes through that area right there enclosed by the path. And so that should allow us to figure out what the magnetic field is. And so the magnetic field around a current carrying wire like this is just mu 0 times I divided by 2 times pi times r. Okay, and so that's the steps we need to use Ampere's law if we can't remember an equation for the magnetic field around the wire. Now, one thing I guess I haven't talked about on either of these two problems is a priori, I guess, we had to believe that the electric field was radially outward. So if I want to write the electric field, I just calculate it as a vector because it is. I might do something like that, okay? Put a unit vector that's radially away. And I'm thinking a cylindrical coordinates unit vector from that axis in the center, which might be the z-axis, right? Make that the z-axis, all right? So radially away is the right answer. This isn't a spherical coordinate radius from a point. This is a cylindrical coordinate radius from a line, the z-axis generally, okay? So hopefully that one makes sense. And let's go look at the magnetic field direction. Again, you kind of have to know a little bit. You can get the magnitude from Ampere's law, but for direction, let's see, we talk about a right-hand rule. And remember, the right-hand rule says that if I put my thumb in the direction of the current, our fingers point in the direction that the magnetic field is, and it is circumferential. It's going around in that path around the wire, and it's going around, I guess, as we're viewing it from the end here where I might put my eye. Okay, I guess I would call that counterclockwise if my eye is, that's a lousy looking eye. But if I'm looking at this thing that way, okay, it's going around counterclockwise. And so that's the direction. And if you're in cylindrical coordinates, we're going to call that phi. Okay, that's the phi direction, or maybe theta if you like, but I'm going to use phi. In cylindrical coordinates, you've got r, phi, and z. Okay, and whether it's plus or minus depends on how I define which direction is the z-axis. Okay, so that's how I might make the magnetic field into a vector. Okay, everybody good with that so far? All right, well, we haven't done a thing with special relativity yet, have we? And so I better get moving, okay? I better get moving. And so here's the deal. I've just put those, equations that we just fit here, we just arrived at for electric and magnetic field on this slide. And so nothing really new here, other than to point out that in the lab frame, okay, which is where we're going to look at this problem first, in the lab frame, okay, the charge densities, these linear charge densities for the negative charges, the blue ones, and for the positive charges are the same, okay? And if that's true, the net charge in the wire, this lambda right here, okay, I've got just as many negative charges as I do positive charges, and so that's equal to 0. And so the electric field is giving me 0. Everybody okay with that idea? All right, but let's take a second now and figure out what the magnetic field is, and then the force on the charge because of the magnetic field. And if you remember, there was an equation we talked about of what current meant, and it was proportional to this thing called the drift velocity, which is this speed that we're thinking about, okay? Very slow, if you recall. Like glacially slow, like millimeters per second, perhaps for high currents. But all of these factors right here, the charge density, the density of the electrons, that's electrons per volume, and then the number of coulombs on every electron, and then the cross-sectional area, that all has units of charge per unit length, lambda. And so that's what we're going to use for current in our magnetic field equation that we just arrived at. And so I guess it's time to figure out for this problem, what is, no kidding, the field and the force going to be. And just, I'm going to make this direction the positive z direction for the purposes of plus phi hat or minus phi hat to denote clockwise or counterclockwise around that z-axis, okay? Because we have to do that for a magnetic field. And so I'll come on to the next page. I might be able to straddle this here for you so you can see what I'm going to do. And I think you have to believe that the magnetic field here is equal to mu zero times I, which is now lambda, that's the charge density for the negative charges, which are moving here, times the, well, divided by 2 times pi times the radius that I am from this thing. And so, of course, the radius would be this distance, I guess, right there, okay, from the center of the wire out to where the charge is. And I should kind of go right up to the middle of the charge. All right, and I think if what we said is true, and I looked down the z-axis, all right, it is going to be a phi for the direction of this thing, phi hat, and then it's going to go as I'm viewing, looking right down the positive v-axis towards the wire, positive z-axis toward the wire. It would be going clockwise around. Okay, well, in polar coordinates, clockwise is negative, so it's in the negative phi hat direction. And I'll just kind of draw you. There's the z-axis coming out of the page at you. We think the direction is this way, right? And that's minus the phi hat direction. That would be plus phi hat. From the x-axis, I guess, going in a counterclockwise direction is a positive angle, and so it's consistent with that. All right, well, now it's time to find that force, the effect on that charge particle, and the force is equal to, as we said, Q times V crossed with B. And I'm being formal here. We already kind of pictured it with the right-hand rule when I was talking a second ago. But let's see, Q times V, well, that's Q times V, and that would be the Z hat direction, because remember, I had the charge moving in the positive Z direction. So I gave it that unit vector. And then I'm going to cross it with, I guess, mu naught, mu zero, the permeability of free space, times lambda, which is really for the negative charges, right? Where did my thing go? Oh, I turned it off. That's why my stylus turned itself off. Let's see. And then I've got over 2 pi times the radius, and then I'm multiplying by a unit vector in the minus phi hat direction. And so you got to do vector multiplication twice, I suppose, whether you like it or not. When I do all this, I suppose I'm going to get Q mu zero, that moving, and Q is the moving charges charge, right? Okay, and then we'll put the other charge, the charge which is in the wire per unit length. And then what else do I guess I have? I've got the permeability of free space up there. And then I've got a V here. What did I drop? What did I drop? You can, hopefully you can see it. Nobody popped up in the chat that I dropped a term here. QV crossed with B. And remember, we said that current is lambda times the speed, so I dropped the speed right there, didn't I? I was talking about the fact that it was negative, the charge density of the negative charges, and I dropped the velocity, okay? And so since I dropped that, that does mean I've got velocity squared right here, and that's all divided by 2 pi r. So that's the magnitude of the force in this kind of basic system, how fast the charge is moving and how far away I am from the wire and some physical constants. The next question, I guess, is direction. That's the other thing you have to do. And notice I'm multiplying z hat times minus minus phi hat. And just like unit vectors I, j, and k are cyclic, like I times j is k, okay? And if you go the other way, you go j times I, you get minus k. In this example, okay, look at my cyclic nature of the unit vectors in cylindrical coordinates. If I multiply z times, I'm sorry, phi times z, I would get r. But if I multiply z times phi, I would get minus r. It's cyclic in that same sense, okay? And if you hadn't known that, because you haven't gotten that in a multivariable yet, you will. Okay, so I guess I'm multiplying z hat times phi hat. That's going to be minus r, but it's a minus phi hat. So this goes to be in the radial direction, which is why I said that the force in the lab frame is going to be radially away from the wire for the geometry we set up of that moving charge. Okay. Remember, this guy was moving to the right. All right, let's shift gears. Everybody good with that? So far, pretty much introductory physics. Here's the kind of wacky part, because now we're going to saddle up that moving charge and ride right along with it. Okay. And so we are seeing that moving charge as a stationary charge in our K prime system, right? That's what we're seeing. And the interesting thing we're going to see here is that the charge densities are no longer the same. Okay. The charge densities are no longer the same. The first question I guess I would ask you in this thing is, are the electrons moving anymore? And the answer, I hope, would be that that no, they're not. Okay, they're not moving. We were able to say, and let me scroll back to it, in the lab frame, in the fixed frame, where was I? I guess in the fixed frame, I was able to say that the electric field was 0, but the magnetic field was not 0 in the lab frame. And now I think I'm going to say the exact opposite thing in the frame of the moving charge. Now the electric field is no longer 0, right? Because these two things are not 0. They don't add to 0 anymore because they're not going to be equal. And we'll see why here in a second. But the magnetic field, I think, is now 0 because does anybody see a current right now? If you're moving around along with that positive charge at exactly the same drift velocity that we're talking about, there's no motion of charge, so the magnetic field is 0. And so now the question, I guess, is what's the electric field going to be? And then what's the force on that charge because of the electric field going to be? Okay, so that's where we're going. And it's just a difference in perspective. And so I guess I have to do a little bit of math here. This is the picture again now, and just to keep you oriented, we're now doing this case, okay? Now this charge that used to be moving looks like it's at rest because we're moving along with it. And I think if you see in this picture, there should be two things represented, one of them not overly well, but you can see that whoever drew this made that distance right there less than it was there. And in point of fact, that's only half of the solution. The other thing that happens is that this distance right here between the electrons actually has gotten a little bit greater. And so all of a sudden, because of that, we've got a net positive charge on this wire, and we get an electric field. And so here's, I guess, the question. Why are those distances different? Well, the answer is we're no longer in the lab frame. One of them is now moving, one of them is not. One of them is length contracted. That would be the positive charges separation between them. One of them is not. One is actually length expanded, and that's the distance in between the negative charges. And so that's the case that I'm going to make. And as a result of that, you no longer have the charge densities of the positive charges and the negative charges being equal to each other. You no longer have 0 net charge density on the wire if you're moving in the frame with that particle that's above the wire. Sort of bizarre. Well, let's look at the math behind it now and see if what I said makes any sense. Okay, and I guess what I have to do is convince you that for the positive charges, and this one I think is easier to make the case And that's why your author, whose figure I pulled off and stole in the moving frame here, okay, it is equal to the same amount of charges, and these are the charges for the I guess if the wire that's made out of copper, it's the copper atom that's missing a electron, right? Those guys divided by the length. But if you look, if you're stationary with the moving charge above, those red positive charges, they are moving. And so my expectation would be that that distance is going to be shorter. It's going to be length contracted, okay? Because it's moving relative to me, and I got a meter stick that measures the distance because I'm moving with it. And so it's going to be length contracted. And hopefully that makes sense. And so this is going to be Q, and then this length here will be what it was in the moving frame, which I guess I would have called the proper length, divided by gamma. And so the result is I've got gamma times what the charge density for the positive charges were in the stationary frame, okay? That's what I guess I got. And if you're trying to write this out, I guess we're gonna write the charge density that was in the K frame, in the stationary frame, and then multiplying by gamma, so I'm going to write it suggestively, 1 minus v squared over c squared. Okay, this is the Lorentz gamma, and that's to the minus 1/2 power, right? This is the square roots in the denominator, and I just chose to write it that way. But okay with that? Nobody's saying but in chat, so we'll assume we're good to go. And now I guess that those were the positive charges, the red ones. What about the negative charges? How's the charge density? And I'm going to scroll up just a little bit to give myself some room here. What's the charge density for the negative charges in the moving frame? Well, it is the negative charges, okay? Same ones that were there in the stationary frame. And this was, if this was the moving frame for the positive charges, the separation between the charges and that for the positive charges, now I guess I've got the separation between the charges, the negative charges this time, in the moving frame. And this is the one I think I have more trouble explaining this, but it's, I think, going to be a little bit bigger than what I measured in the lab frame. If I've convinced you that the protons, the base copper without an electron, those holes, I guess, those are moving and are therefore length contracted. I think you kind of have to believe that in this case, this has gotten a little bit bigger than it was in the lab frame by a factor gamma. Okay. All right. So the lab frame compared to this is actually length contracted. Okay, that's how I would view this. If I'm saying I'm moving with these negative charges right now, I'm saying that I'm now in the proper, I'm making a proper frame measurement. And that lab frame that we used last time that we called L0, well, that's got to be the length contracted thing. So in order to find the moving frame, I got to multiply by gamma. All right, well, that means the charge density then is 1 over gamma times what the charge density for the negative charges was in the lab frame. And so here I've got lambda, okay? And I guess I should have maybe subscripted that positive and this negative in the lab frame. But now I'm going to be multiplying by 1 over gamma. And so that means the gamma comes up in the numerator, or gets a reciprocal. This 1 minus v squared over c squared factor is now in the numerator, and so I just raised it to the positive 1/2 power in this case. Remember, this was to the negative 1/2 power there. Okay, and just before I scroll up a little bit, remember what my equation is for the electric field. It's the sum of these two guys. That's the overall charge per unit length divided by 2 pi epsilon 0 r, right? That's the deal, okay? We're going to come to a quick conclusion here, I guess. What is lambda net? Okay, well, I guess it's the sum of these two things, but the negative ones are negative, right? Those are definitely negative. Let's cut to the chase. How am I going to add these up? Because these are two wacky expressions. Here's what I'm going to do. I'm going to call that first one lambda plus, and then I'm going to use the binomial expansion for about the 5th time. And so remember, that'll be plus 1/2 v squared over c squared, okay? Yeah, I showed you the binomial expansion theorem in case you forgot. I'm doing this right here, okay? That you bring that guy right down there because of this rule. And so that's why I wrote that. 1 plus v squared over 2c squared. Let's slide back up again. Okay, so that's what I wrote. And then I've got to add on to that the charge for the negative charge density, but it's negative, so that's minus lambda, okay? And I should just, since I've decided to make that negative, I made it the negative of the positives, I suppose, and I'm going to make this 1 minus 1/2 v squared over c squared, again using the binomial expansion theorem. Cancels, right? And what I'm left with then, 1/2 minus a minus, so it's 1/2 plus 1/2, that's a whole. What I'm left with is the charge density of either one when they were equal in the lab frame. So I can just drop the subscript plus or minus altogether, v squared over c squared. That's the difference, isn't it, between the charge density of the positive and negative charge, only because of length contraction and length expansion, I guess, compared to the lab frame in the moving frame. Let's keep on here because I got to wrap this in about 2 minutes, which is going to just about work out okay. What does that mean? That means that the electric field, which we said was the net charge density, right, divided by 2 pi epsilon 0 times r, and it was in the radial direction, would be equal to lambda v squared. That's lambda now in the stationary frame, right, as opposed to the moving frame here, because this is actually, I guess, moving. All right, divided by 2 pi epsilon 0 r hat. Oops, what I forgot. I forgot the c squared, didn't I? Okay, great. And so what's that going to mean for me? That means, I guess, if I'm trying to find the force is going to be that moving charge that was outside the wire times the electric field. And so it's Q times lambda times v squared divided by 2 pi epsilon 0 c squared times r, and that was times r hat. All right, here's the deal. In like 1 minute left to go. Is that the same? That's an electric force in this frame. How does that compare to the magnetic force that I found in the other frame, in the lab frame? And I got to go to the finger pointer. And there it was. Okay, remember this was a magnetic force. And it looks similar. I got Q lambda mu naught v squared over 2 pi r. So I got the things that are the same, I think, are the 2 pi r. I got the v squared, which is the same. I got the q and the lambda, which are the same. But I got mu naught here. And let's see what I got in the other, when it's an electric field. When it's an electric field, I don't have mu naught r, mu naught. Instead, I have c squared times the permittivity of free space. But that's okay, right? Because c squared is equal to 1 over the permeability of free space times the permittivity of free space. Okay, so when I multiply that by the permittivity of free space, I have 1 over the permeability of free space. So that thing right there becomes exactly q lambda v squared with that mu 0 divided by 2 pi r, and it's in the radial direction. And now the electric force in the moving frame is exactly the same as the magnetic force in the lab frame, in the stationary frame. A little bit spooky, but that's the way it works out. All right, I'm done, and I took exactly, why do we multiply by gamma this time? Okay, and that you're talking about in the charge densities, right? And so let's just back up real quick right here. And I think our book's picture is misleading, but I want, nope, where do I want? What picture do I want? I want to show you this sketch right here, okay? And what I'm proposing is in the lab frame, I had this length right there, right? In the moving frame, I have this length right here. If I call that 0, this one is certainly length contracted, okay? And that caused me to do one thing to gamma, not shown in your book, but I think these guys actually get further apart. Okay, and so that's why I have to, it cannot possibly be the same as this case up here in the lab frame. It has to have changed. And if I divide it by gamma with the positive charges, I have to multiply by gamma for the negative charges. Okay, in neither of those distances can possibly be the same as they are in the lab frame. Hopefully that makes sense. Any event, so we're done with, yes, indeed, electromagnetic fields, or at least the forces that the charges experience, the pushes that they experience due to electromagnetic fields, can be described either as a magnetic field in a stationary frame or as an electric field in a moving frame. Okay, they're the same. I'm going to get the same push on the electron or in the positive charge that's moving, whatever it is. And that's the brilliance of Einstein. He's the one who saw there's really no such thing as a difference between an electric or a magnetic field, or at least the effect they came. Yeah, I agree. It is. It's crazy. It's just a matter of which reference frame you view it from. But the force is the same. Okay, it is the same. Now, you're going to have a worksheet problem to do. And one of the questions I just want to give you a hint on is I ask you, okay, what is the difference in the, what is the difference? There it is. Sorry if I'm spinning your head there. What is the difference in the net charge? And I've kind of left you with an equation. This is the thing you should be looking for, right? You don't have to go through the binomial expansion theorem for yourself for this is actually the last problem on the worksheet, okay? But that is the difference between the two in the moving frame. And so you can jump right to that equation. All right, everyone, I've kept you now 4 minutes answering that question. The downside of me doing a more traditional lecture is the worksheet is on your own time, and of course, it's due on Wednesday. You also have a homework in WebAssign due on Wednesday, so you got a little bit of work to do between now and then. Normally, I'd give you more time right now. It just didn't work out that way. Questions? Hey, everybody have a great day, and we'll see you on Wednesday. And mind-blowing, absolutely. Just sort of a bizarre thing. Who figured? And so when you hear people talk about electromagnetic fields, this is why. Just a matter of frame of reference. We'll see you then.
Thank you. I have a question.
Sure.
Will we have a pre-lecture video for Wednesday?
Yes, I would expect one. Yeah, and it should be much shorter.
Okay, perfect.
Yeah, and I should now stop recording here. If I can find, where is it? Where is it? Stop recording. Where's stop recording? There it is. And so I'll be posting this up on Canvas too if you want to review what I've said here.